Exercise 128 is asking you to do two things. First, identify the hybridization state for each of the carbons in this molecule here. And second, identify the geometry. And this is a very special molecule. This will often come up as an exception when you learn general rules in organic chemistry. One thing you might notice in this molecule is that this has a lot of double bonds, and it's also in a ring. Both of those features add rigidity to a molecule. Because like if you have a straight chain of molecules, like carbons that would just go in a straight chain, all of those bonds can rotate. And so at any given moment it might be this shape, or it might be this shape, or it could squiggle around like a piece of spaghetti with all single bonds. But when you have double bonds, those can't rotate. And so they're stuck in exactly that position that they're in, the carbons. So that's one thing. The double bonds add rigidity, and rings, of course, also add rigidity because the atoms can't just move around. They're stuck in this ring. So because of the double bonds in the ring, benzene is a very rigid molecule. And because it's very rigid, it very reliably fits into pockets on receptor sites in living things. It's often used in medications or in neurotransmitters or in hormones, because all of those things are molecules that need to reliably fit into receptor sites, and for that you need a rigid molecule, and benzene is a beautiful example of that. So it's an exception that we'll run into a lot. In this question, though, they're just like introducing you to benzene and trying to get you to think about the hybridization on the carbons and also the shape around the carbons. So let's pick a carbon. I'll do this one right here. If you notice, all of these carbons are symmetrical, so they're all kind of in the same scenario. And in these, you have the first bond you ever form is a sigma bond, so you have one sigma bond, two sigma bonds. Every bond after the first bond is a pi bond, so here we've got one pi bond. And if you notice, around this carbon, there is just one pi bond, the purple one that we drew. And so if you have just one pi bond, the atom is sp2 hybridized. So that carbon would be sp2 hybridized. And we went through the reasoning behind that in previous videos for previous exercises. So that's sp2 hybridized, and if you notice, every single carbon around this ring has just one pi bond attached to it. And so all of those carbons are sp2 hybridized. All 6 of them. So that takes care of the first part, identifying the hybridization state of these carbons. The next thing is to identify the shape. I'm going to erase these to leave some space here, make it look a little simpler and clearer. Let's try to find the shape around one of these carbons. Now if you notice, all the carbons are in a symmetrical relationship, so they're all going to have the same shape. I'm just going to pick this one over here. And we want to ask ourselves, how many atoms is that bonded to? Well, 1, 2, 3. So that's bonded to 3 atoms. And how many lone pairs are around that carbon? I see no dots there, so we're looking at 0 lone pairs, and those two things pair up when they all repel each other to give you a shape of trigonal planar. 3 atoms and 0 lone pairs. And so this carbon here, is trigonal planar. So flat, in a plane. And since all these carbons are symmetrical, all of them are going to be trigonal planar. And so this whole molecule is going to be planar. It's going to be flat. And that is just another feature that makes it very special. It's rigid and it's flat, so it's going to fit into very particular enzyme sites or receptor sites very reliably. So you can go through it yourself. You'll see that for every single one, you'll end up with this same arrangement. Every carbon in this molecule is sp2 hybridized, and every carbon in this molecule is has a trigonal planar shape. around it.